Neha apologizes that she can't be here. She had a family issue, and you're probably disappointed to not see her. I know that I am. So we are comparing semi-volatile and water-soluble organic precursor gases. And the reason is because we're interested in secondary organic aerosol formation. So the way that we typically understand SOA formation, the way that we describe it in models, is that there are emissions of volatile organic compounds, and in the gas phase, they can be oxidized, and some fraction of the oxidation products decrease in volatility, and so we call them semi-volatile organic compounds. We can use a two-product ODA model, we could use more products. And because like dissolves into like, these semi-volatile organic gases will condense to a pre-existing organic aerosol matrix and contribute to the particulate matter burden of the atmosphere. And a corollary to that is that same exact gas phase photochemistry will produce water-soluble organic compounds. So a high fraction or a large amount of the oxidation products are small polar compounds. And because like dissolves into like, if an organic compound has polarity, it will partition to a polar solvent. And liquid water is a ubiquitous and abundant polar solvent. And globally, aerosol water dominates over organic aerosol mass. So this idea was motivated in part by a modeling study we did for the continental United States, where we evaluated the chemical potential for a water partitioning pathway and a semi-volatile absorptive partitioning pathway. So on the left-hand side, these are average water-soluble organic gas concentrations for gases that were shown to form SOA through a wet chemistry process, and they can partition into this medium. And then this is the average semi-volatile organic gases, and they could partition into this medium. So the modeling work suggested that this water pathway had a higher potential, in particular for the Southeast United States, than a semi-volatile partitioning theory. So we wanted to see if that was true. So one of the first things that we did is we updated to the newest version of CMAQ that we could. We used CMAQ version 5.01, and to get started, we've just been modeling the same 10 days over and over again. We used the SAPRAC 07 gas phase chemical mechanism, but we used explicit, what passes for explicit chemistry in a photochemical model based on the work by Fabian Pelot. We also had heterogeneous organic isoprene chemistry, so the IPOX chemistry, and that's based on a paper by Havala Pai. We used WRF and BICE, and for these first simulations that we're going to describe, we used emissions from the 2008 NEI that were grown to 2013. So it's basically NOAA's forecasting runs. And we did this for the whole entire continental United States using a 12-kilometer by 12-kilometer grid. So we separated the semi-volatile species. These are the first and second product compounds that you would use in an ODAM type model. So for example, if you're familiar with CMAQ, this would be all the semi-volatile xylene 1, semi-volatile xylene 2, et cetera. And for the water-soluble organic gases, we summed up all of the gases that have been shown in laboratory experiments to form SOA through an aqueous phase process, or for which we have ambient evidence suggesting that they do. And we find the same trend when we evaluate it for the surface or for the whole entire model. So in these simulations, the model goes up to 50 millibars. And the water-soluble organic gases are on average an order of magnitude higher than the concentration of the semi-volatile organic gases. This is the vertical total, and this is for the surface layer. And then we extracted the model predictions for the SOAS site in Centerville, Alabama. So the x-axis is time, so the 10 days for the simulation. The water-soluble organic gases are on the first y-axis, and the semi-volatile organic gases are on the second y-axis. And again, we see that in Centerville, Alabama, the model predicts about an order of magnitude more water-soluble organic gases than semi-volatile organic gases. I went the wrong way. So, when Neha went to the Southern Oxygen and Aerosol study, what we wanted to do is we wanted to scrub water-soluble organic gases from the atmosphere, bring them back to the laboratory, and do typical SOA experiments in the lab. And so we had 4 mist chambers operating in parallel, and she scrubbed water-soluble organic gases from the air. The samples are composites for 4 hours, and she did 2 to 3 runs per day. The flow rate was 25 liters per minute. And what we're doing is we wanted to compare our initial samples for total organic carbon with what the model was predicting. So an analogy would be people often will evaluate models for total VOC reactivity, and we wanted to evaluate the model for total VOC solubility. And so again, the x-axis here is time, and then the y-axis is CMAC, water-soluble organic carbon predictions, and then the second y-axis is what we measured in those initial samples for total organic carbon. So what we see is that the model is not completely out to lunch. When CMAC predicts a lot of water-soluble organic carbon, we tend to measure higher amounts. And when it goes down, we measure lower amounts. The mist chamber samples are aggregated over time, so that's what the width of these bars represents. But the model's not perfect either. So we imagine that we took these mist chambers, put them into CMAC's atmosphere, and sampled from CMAC's atmosphere the same way that we did in the ambient environment. And when we try to compare the CMAC predictions of water-soluble organic gases, where we took every single organic gas and estimated how much we thought would be collected by our mist chamber, and then compared that to the measurement, here's the one-to-one line. And the model's not really capturing that well. But when we blow it up, we see that the model's not totally out to lunch. There is some relationship, but we're not capturing quite well. So we're doing a variety of collection efficiency techniques for the gases that we think are there. So we were interested to see what are the water-soluble organic gases that the model thinks are driving this. So we see the usual suspects, glyoxal and methylglyoxal have high concentrations predicted by the model. And then another two, next two organic gases that had the most were the HMML and the May compounds derived from isoprene oxidation. But the overwhelming majority of the water-soluble organic gas predicted by the model to be present is IEPOX. This scale is about an order of magnitude higher than on the previous slide. And then, but the majority of the water-soluble organic gases are in the model species called RCHO, which means aldehydes that are not glyoxal, methylglyoxal. So most of the water-soluble organic gases, most of the potential for that water partitioning pathway is simply uncharacterized by the most explicit gas phase chemistry that we can model with currently. Just for comparison, the semi-volatile materials that contribute the most, all of the aromatic semi-volatile species added up together are less than any individual biogenic species. So these are semi-volatile products from sesquiterpenes, semi-volatile products from isoprene, semi-volatile products from monotropine, and then all of the aromatic species added together. And another thing that we spend a lot of time thinking about is it's not just how much abundance you have of a water-soluble organic gas. It has to be co-located in space and in time with aerosol liquid water. And so we're always thinking about the potential of an organic gas to contribute to particle mass, actually. And so here, what we've just taken is, when we think about the water-soluble organic mass potential, we just took the Henry's law constant and then converted that to how much would be present in the liquid water available at the time that the gas was there. And what we can see is that IEPOX really dominates, and glyoxal and methylglyoxal are just don't even show up when you plot them on the same scale. And this is very consistent with a recent paper in Environmental Science and Technology Letters, where they found that IEPOX was a dominant SOA contributor. So at the SOAS ground site, CMAC still predicts water-soluble organic gases are more abundant in the atmosphere as compared to the semi-volatile counterparts. The CMAC model trends for water-soluble organic gases follow the mist chamber measurements at the SOAS ground site, but the measurements are substantially lower than the CMAC predictions. And this could be a collection efficiency issue, and we're still investigating that. The CMAC simulations predict that IEPOX is the most important water-soluble organic gas for partitioning, and that's consistent with independent ambient work that's recently taken place. We've just started to model the whole entire SOAS campaign. We recently finished our 2013 emissions, and we plan to evaluate total VOC solubility using Rodney Weber's WSOG pills measurements. Another thing that we've started to do, and I encourage you to go see Eleanor Waxman's poster, is we started to account for salting in and salting out based on aerosol molality using well-established Sensical relationships, and her poster is very exciting, so you should go see it. Neha acknowledges her colleagues in the Carlton and Turpin research groups. Rob Pender and Havalapai shared beta versions of their code with us, and we thank all of the SOAS participants and kind support from a variety of agencies. Thank you.
Thank you, Anne-Marie. We have questions? Yes, let's say.
Have you thought of, instead of running the NCM and running the outputs, will you do that?
Yeah, that's a good idea. Yeah, we should do that. That's a great idea. Yeah.
One thing you didn't mention was the organic acids, formic, acetic, and oxalic acid.
Yeah. So the SABRAC-07 gas phase chemical mechanism has RCOOH, which stands for organic gases. So one thing that's really exciting, and I didn't touch on it at all, is we originally had done aqueous experiments to form SOA using known precursor gases in the laboratory. And then the idea from SOAS was to scrub the gases and do the same exact experiments. And we make the same carboxylic acids that we always make, oxalic acid, pyruvic acid, glycolic acid. But we don't really observe those in the particle phase during SOAS, but we do observe them in the gas phase. I can talk to you about why I think that is offline.
Yes. Jeff.
Typical linear aldehydes aren't particularly soluble, but once you start putting functional groups on there, they do become soluble. So I'm just wondering what was assigned to these generic aldehydes that come out of the model in terms of Henry's law?
Oh, yeah, that's a great question. So gas phase chemical mechanisms will organize species based on their reaction rate constant with OH. So if you go in and you look at aldehydes that are, say, being mapped to generic aldehyde 2, say, their reaction rate constant with OH will vary by less than 10%. But their Henry's law constants will vary a factor of 40,000 sometimes. And so then you pick an average value and it represents nothing sometimes. And so I could tell you what's in the model, but I think all the aldehydes that are not explicit map to all the acids that are not explicit map to adipic acid, and then all the aldehydes may be mapped to glycoaldehyde for deposition calculations and stuff.